All right, good morning, everyone. Today we are starting off with the building blocks of geometry. So it's going to feel a little bit funny that we're in a math class where we start off with so much vocabulary, but that's where we start off. We start off with vocabulary for all of our figures, and we go over notation as well as real-world examples. So first up, we're looking at three undefined terms. So our three undefined terms will be the point, a line, and a plane. So such figures do not really exist, but we can represent them with objects in the real world. So when I start off with a point technically has no size. Okay, but we visualize it as the tiniest little fleck we can possibly imagine, so we represent it with a dot. Okay, so again, a point has no size, but we represent it with a dot. So here in my visual, this would be, here's that little dot with an uppercase A right next to it. This represents point A. And note that the A must be a capital. So when we're identifying points, we identify them with capital letters. So here is a little dot, a little A next to it. This is point A. Okay, another way that we could visualize a point would be with the intersection of two straight pathways. So let's say that I put down here a little toothpick and another little toothpick like that. So that point right here is the intersection of these two straight pathways. So I could also have a point right here. I could call this point B, for example. Just another way to visualize a point. Okay, some real world examples. Here I've already written them off to the side for you. We have freckles, a period at the end of the sentence, a star, a grain of sand. I'm sure you can come up with more. We're just trying to visualize just the tiniest little fleck you could possibly imagine. That would be a point. So again, points have no size. We represent them with a dot. In notation, we write the word point and we include a capital letter. Okay, next up, here we're looking at our lines. So a line has no thickness. Okay, and when we imagine it, we are visualizing that it extends in both directions forever. Okay, so you are visualizing just the thinnest straight pathway you can possibly imagine. Technically, a line has no thickness, but it extends in both directions forever. So here in my visual, I've included 2 points on this line, so I can name my line using any 2 points on the line. So I could say AB, double arrow on top. A and B can be any 2 points on the line. The order doesn't matter. I could also write BA, double arrow on top. So again, the order doesn't matter. These just have to be any 2 points on the line. So technically, since our lines are continuous in both directions, there's really an infinite number of points on that line. So imagine that I threw in another point here and call it point C. Well, I could name this line AC or CA, CB, BC, AB, or BA. I just have to put a double arrow on top. So it just takes any 2 points on the line in order to name it. The order doesn't matter. Okay, in my second visual, here I'm showing a line and I haven't put any points on it, even though I'm sure they are there. So here, this is just a more stripped down visual where we're just looking at the line, and then we put this little lowercase letter off to the side. So if I had many different lines in the same visual, this just gives me a nice, easy way to identify it using this lowercase letter. So I would name this line, line, lowercase m. So I just want to be clear that that m is lowercase. So again, a line has no thickness, yet it extends in both directions forever. So you're looking at anything that you can picture as the thinnest straight pathway. It's just continuous in both directions. We can name it by any 2 points on the line, order doesn't matter. Okay, or we can name it by a lowercase letter off to the side. Okay, some ways to visualize in the real world. You can picture the equator on a map, since it's going to keep extending in both directions. Okay, I also like to picture a scarecrow with their arms extended, pointing in both directions. So again, these are just ways to help us visualize lines. Okay, and then any points that are on the same line, on the same straight pathway, are collinear. What's really helpful about that is that it has the word line embedded within it. So any points that are on a straight pathway on the same line are collinear points. Okay, could be 2 points, could be 10 points, could be 25. Any points on the same line are collinear. Okay, the last of the undefined terms is the plane. Let me slide this up. Okay, so a plane has no thickness. And yet it extends in all directions forever. Okay, so what we're picturing in our heads, we're picturing the thinnest, flattest surface that you can possibly visualize, and then you're just picturing that it extends in all directions forever. So here I have this tiny slip of paper in blue, right? This could represent my plane, right? I've drawn it, or I've created it as kind of this rectangular shape, but you really want to imagine that it keeps extending in all directions forever. So it's not just this contained sheet of paper, it's a layer. It's like when you are in a building and you're on a floor. That floor is a layer. That is a plane. So here is my plane. That's how I'm trying to visualize it. It extends in all directions forever. Okay, the way that we visualize a plane, we usually draw it looking like this parallelogram shape. But again, remember, it's continuous. It keeps extending in all of those directions forever. So here we can name it by any 3 non-collinear points. So we have to make sure that it's non-collinear and any order of 3 non-collinear points. So I can name this plane CAT, or CTA. Those are 2 options. Okay, another 2 options. I could have plane ACT or plane ATC. Okay, that's another 2 options. And I have 2 more options here. So plane TAC and TCA. So again, this is any 3 non-collinear points. Okay, so any 3 non-collinear points. So let me make clear why it has to be non-collinear. Let's say that I look at here. Here's my little tiny toothpick. So if I pick 3 points that are on this same pathway, that are collinear, then I could have this plane that contains them, but it could also be this plane that contains them. It could be this plane that contains them, right? I have really an infinite number of planes. I'm just rotating my hand to help you see it. I would have an infinite number of planes that would slice through those 3 non-collinear points, okay? Or those 3 collinear points, sorry. So since these 3 points in my model, here, 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 were on the same line, right, there's an infinite number of planes that could contain them. Okay, but once I spread it out, so let's say that I have a point here, and then I have a third point over here, then there's only 1 plane that could contain them, right? There's no more than 1 plane that could contain those 3 non-collinear points. Okay. All right, so then again, another way that we can name a plane, sometimes we don't show all the points even though they are there. There's an infinite number of points on that plane. Sometimes we just draw a more stripped down visual and we use this script capital cursive letter off to the side. So I could also name this plane with a capital cursive B. So I want to stress that this is a capital script or cursive letter to help us identify that it is a plane. Okay, so a plane again has no thickness. It extends in all directions forever. When we name it, we can use any 3 non-collinear points. And the reason that they have to be non-collinear is we want to make sure that it's clear that there's only 1 plane that could contain them. So if I have 3 points like this, picture the tips of my fingers as 3 points, right? There's only 1 plane that could slice through those 3 points. Once I put them on the same straight pathway, so if I put 3 points here, 3 collinear points, then I would have an infinite number, let me use a different color, I would have an infinite number of planes that could slice through them. So I'm just trying to show you that. Maybe I'll tilt it like that. It's probably an easier way to see it. Okay, and then some real world models. We could picture the whiteboard. We could picture a window. We could picture the floor. We could picture the surface of a desk. All of these are good representations of a plane. So again, no thickness, extends in all directions forever. We can name a plane using any 3 non-collinear points or by a capital cursive letter that's often off to the side. Okay, and then here again, one more vocab word. Points that lie in the same plane are coplanar. And what's helpful about that is the word plane is built in to the word. So any points that lie in the same plane are coplanar. Could be 2 points, could be 10 points, could be 25 points. But any points in the same plane are coplanar. Okay, again, these are the 3 undefined terms, the point, the line, and the plane. Okay, let's look at the second sheet of paper, and we're going to look at the 3 defined terms. So here is that second sheet of paper. Let me just slide it down. Okay, so now we're looking at 3 defined terms. These figures are defined in terms of the basics. Our basics are the undefined terms. It's our point, our line, and our plane. Okay, so we're starting off with a segment. So a segment is a portion of a larger line. It just has 2 endpoints. So a segment is a portion of a larger line with 2 concrete endpoints. So here in my visual, right, I've drawn a segment. I have 2 concrete endpoints, but I can visualize that this was part of a larger line that would have extended in both directions forever. I'm just capping it between points A and B. So when I name a segment, I name it by the 2 endpoints. So here I would have AB, with a little dash over it, or BA, little dash over it. Order doesn't matter. We simply define it by the two endpoints. Okay, some real world examples. So we're just picturing straight pathways that have distinct endpoints. So a pen, a ruler, the edge of a desk are great examples. Okay, next we're looking at a ray. A ray is also a portion of a line, except this time we have one endpoint and it extends in the opposite, the other direction forever. So a ray is a portion of a line with one endpoint extending in the other direction forever. Okay, so in my first example, here we go. We have this ray. I can see that it was part of a larger line, right? I can visualize how this side could have been continuing on in that direction forever. So when I name a ray, I always start with the end point. Here's my end point. And then I can use any other point that it passes through as it goes in that other direction forever. So I would name this ray H, that's the end point, and then the G with an arrow to the right. So I just want to be super clear that the H, that's where we have the end point first. And then the G, right, this is any other point that it passes through as it goes in that direction forever. Okay, so if, let's say that I had put in an extra point here just for the sake of example. Let's say I put an O right there. I could have named this ray HO with an arrow to the right or HG. That would be fine. They would both name the same ray. I just need the end point first and then any other point that it passes through as it goes in that direction forever. Okay, what I could not do is I could not name the ray OG. OG would be O is the end point and it extends in that right-hand direction forever. Okay, another example here. Here I just drew my visual with the ray extending to the left. When I write it with notation, I still do the end point first. So O goes first and then P next. Arrow to the right when I'm writing it. So again, I always have the end point first and then any other point that it passes through as it goes in that direction forever. Okay, and then here, one more example. I just drew a line like this. And what I wanted to show you, I'm going to block out this part and picture C as an end point. I wanted to show you that CA, arrow to the right, and CR, arrow to the right, are the same ray. Because it's the same end point, it's just showing that it goes in this right-hand direction forever. Okay, another example, let me just block off this point and I'm going to view R as the end point. So I'm looking at R as the end point and it's shooting left forever. I can name the ray RA, or I can name it RC. They are the same ray. So two ways of naming the exact same ray, because it's always the end point first and then any other point as it goes in that direction forever. What I also wanted to point out here is let me picture A as the end point, A right there. If A is the end point, I have a ray that's going to the left here and I have a ray that's going to the right here. Those are opposite rays. So ray AC and ray AR are opposite rays. Okay, and opposite rays mean that they have the same vertex or same endpoint, but they extend in opposite directions. Okay, so again, when we are naming rays, we name the endpoint first, and then any other point that it passes through as it goes in that direction forever. We also know here in this last visual that if A is the endpoint, we have a ray that's shooting to the left and to the right. They are opposite rays. They share the same endpoint, but they extend in opposite directions forever. Okay, some real world examples. Picture a laser beam, ray of light, the trajectory, the pathway of a bullet. All of those we're picturing as having a concrete endpoint and going in one direction forever. All right, one little note I also tucked in here. Since segments and rays are portions of a larger line, points that lie on the same segment or ray are also collinear. So collinear points on the same line. So anything that's a straight linear pathway, it could be a line, it could be a ray, it could be a segment. Those are just portions of larger lines. Any points that are on the same ray, segment, line are collinear. All right, one last figure. This is the last of the defined terms. So an angle. So an angle is simply two rays that share a common endpoint, and we call that endpoint the vertex. All right, so two rays that share a common endpoint, the vertex. So here in this first example, I can see that where N is right there, that's the common endpoint, that's the vertex. I have this ray and I have this ray. So when I name my angle right here, I can name it using a three-letter notation. Okay, I can use ANT, for example. That would name it. So I'm using a three-letter notation. I'm using a point that's on each ray, and I'm keeping the vertex, that common endpoint, right in the middle. So then I could also name it angle TNA. So both of these are a three-letter notation. The vertex is right in the middle, and I'm picking points on each of the two rays here. Okay, again, I just want to stress that the vertex is in the middle. Okay, another way that I could name it is simply just by the vertex. So if I only have two rays that share a common endpoint, I can name it by its vertex. But say that I had another ray that extended. Let me use my toothpick to model that, just like that. Okay, I can no longer use the singular letter notation. So I can name it angle N if my diagram looks like this, if I have exactly two rays that share that common endpoint. But if I have more than that, I can't name anything angle N because I don't know which angle we're talking about. Do we mean this small one, or this big one? So that's why we use the three-letter notation in the first place. Okay, in my second visual, I haven't marked any points on these two rays, so I have no choice. I can only name it by its vertex. So angle A for this one. But again, I can't use that notation if I have more than two rays that share that common vertex. So if my diagram looked like this, I couldn't call it angle A because I don't know which angle we're talking about. This one, or that large one right here. Okay, and then lastly, sometimes we get some intricate diagrams where it's just easier to label an angle with a number in the interior. It's not talking about its measure, it's just talking about this angle is angle 14. Angle 14. And that would be fine. So you can name it by a number that is marked in the interior as well. So for angles, we have two rays that share a common endpoint. That common endpoint is the vertex. We can use a three-letter notation like we're seeing here. Vertex just has to be in the middle. We can name it by its vertex here, angle A. We can name it by a number in the interior. Okay, some real-world examples. You can picture hands on a clock. You can picture a wedge of cheese, a slice of pizza, the corner of a desk. All of those examples are two rays that share a common endpoint, which we call the vertex. So again, we have three defined terms, our segment, our ray, our angle, which are built up of those foundational basic terms, those undefined terms that we saw on that first sheet, our point, our line, and our plane. So lots of vocabulary for you today, lots of notation, and some real-world examples as well. All right, have a good rest of your day.